So the first part about the curve sketching, just things really that a lot of this we should know, what we should notice when we're looking at equations. So the basic curves, if you know what a basic curve looks at, you're most of the way there to drawing the graph, because it might just involve a shift or something like that. And so the equations, obviously straight lines being the most basic, so y equals x being the most basic, I guess, straight line. How do we recognise it? Oh, look, both pronumerals to the power of 1 there. Hopefully we would recognise a straight line. Parabolas. Oh, my goodness. One of the pronumerals is now to the power of 2. Quadratics will always produce a parabola. And then in general, we know our parabola is ax squared plus bx plus c. And we did a whole heap of stuff on quadratics, you know, finding the vertex and the roots and maximum points and so on. Cubics. Then again, y equals x cubed. Not all cubics look like our basic one there, of course. Only the ones that can be factorised to be a perfect cube does. The other ones have 2 turning points. So they have the up and down. And so one of the pronumerals be to the power of 3. And so there's our general cubic. And of course then we looked at polynomials in general and how to sketch polynomials. Hyperbolas. So the basic one that we first see, of course, is ones like y equals 1 on x, or x times y is equal to 1. So what are we looking for? You see a pronumeral in the bottom of the fraction, you've probably got some sort of hyperbolic function there, some sort of asymptote happening. Or if you see pronumerals multiplied together, that sort of thing. Then the exponential curves. So that's easy to pick. Hey, there's a pronumeral in the power. That's probably going to be an exponential. Circles, so x squared plus y squared is the radius squared. Both the pronumerals are now squared. But not only are both squared, the coefficients are the same, because then when we looked at conics, we saw ellipses where the coefficients were different. We ended up with an ellipse. And if it was a negative between the two, actually it turned up being a hyperbola, but in a different orientation than we were used to seeing. Logarithmic curves. Our exponential curve, basically the inverse of it. So y equals log. How do you tell that one? Well, the word log's a bit of a giveaway. Okay, same with our trig ones. We know our sine and cosine and tan, and then we end up doing the reciprocal ones as well, secant, cosec, cotan. And then we ended up drawing our inverse trig graphs. So they're all the different types of functions that we've looked at over the past, well, as we say, 18 months. Some other ideas we've been using in curve sketching, if you notice, they're odd and even functions, because that tells you about symmetry. Right? So that makes it easy to sketch. So remember, odd function negative x is equal to negative function x. So they're the ones, rotational symmetry. Even function negative x is equal to function x. So that has line symmetry about the y-axis. When we're dealing with inverse functions, you might remember we talked about symmetry in the line y equals x. If it was its own inverse, so you could swap the x and y's around, then it was symmetric in the line y equals x. So swap the x and y's around, you got the same thing. So something, well, x cubed plus y cubed equals 1 would be an example of that. So I swap the x and y's around, I'm going to have y cubed plus x cubed is 1. Same thing. So we would have symmetry in y equals x. Y equals 1 on x, again, our basic hyperbola. Swap the x and the y around, x equals 1 on y. Well, we could rewrite that, and actually we have got the same curve. Dominance is another idea. We probably don't know if we've talked about dominance in that much detail. This is more when you've got, I guess, a couple of functions multiplied together or divided by ones. Which term will dominate the overall function? Now, so as x gets large, so it's what's happening out at infinity and back at negative infinity, will a particular one dominate? Now, something like an exponential is going to dominate, because as x gets bigger, e to the x gets bigger really quick. So if you've got e to the x times, say, sine x, the e to the x is going to dominate. And that's probably going to tell you what's happening out at infinity. Basically, with dominance, you're looking for the term that rises the quickest, gets the steepest the quickest. Polynomials, in a polynomial, the leading term will always dominate. And that's why, if you remember, when we were sketching polynomials, we looked at the leading term and said, hey, where does that start? Where does that finish? Because because what we were basically saying is, what does that leading term which dominates do out at infinity and negative infinity? So that actually was a dominance idea. We didn't actually call it that at the time. So x to the power of 4 plus 3x cubed minus 2x plus 2. To work out where to start that graph, I just need to think about, oh, well, what does x to the power of 4 do? Oh, it starts up here. It finishes up here. So that's what this curve will do. As I say, exponentials will always tend to dominate because they do rise so rapidly. In general, as again, the one that increases the most rapidly, or which is the steepest, is going to be the term that dominates out at infinity. Okay. And if you're unsure, well then just check by substituting in a large number and see which one's bigger. Okay, then we looked all about asymptotes. So we had vertical asymptotes. Bottom of the fraction can't equal 0. Okay. Horizontal or oblique asymptotes. That happened most often, we saw, with polynomial type ones, where we had a polynomial over a polynomial in a fraction. And so the top of the fraction is constant. We know the fraction can't equal 0. So that would one way of looking at it. But then we also looked at things like limits. That is a way of working them out. Polynomial division, as I've mentioned there. If that order of the numerator is greater than the order of the denominator, do the division. Curves are allowed, remember, to cross the horizontal or oblique asymptotes. It's the vertical ones that they can never touch. Okay. Our special limit, which we often forget, but we saw it, technically it was in 2 unit, when we were proving how to differentiate y equals sine x, this one here. It's technically in 2 unit. They don't ask questions about it in 2 unit specifically. In 3 unit they do, of course. But when it comes to some fancy curves in 4 unit, that could come in handy just to keep remember. So if you've got sine x divided by x or something like that, you know that as x approaches 0, that's going to be approaching 1. So some of the harder ones, you never know, that might come in handy. Don't forget calculus though. We've done all this work on calculus in this course. This actual topic originally was curve sketching without using calculus. Still a really good tool that can be used. So if you're unsure, so you can find your stationary points, your critical points, your inflection points. Yep. So what's a critical point? Remembering, that's when the derivative is undefined. So if it's undefined, most probably we're going to have a vertical tangent, because what we're really saying is the slope at that point is undefined, usually because you've got 1 over 0, which we like to think of, I guess, as an infinite slope, so it'd be a vertical line. Stationary points are also critical points. We don't tend to call them critical points because they have their own name. So technically, critical points are undefined or equal to 0. See? But we just usually think of the critical points as the undefined ones, the stationary points when the derivative is equal to 0. So there might be a maximum, could be a minimum, might be a horizontal point of inflection. Okay, so then our maximum and minimum turning points. So when the derivative is equal to 0, we know we've got our stationary point, but if the concavity is positive, then we must be at the bottom of the curve, so we know we've got a minimum turning point. And if the concavity is less than 0, we have a maximum turning point. Now, if you're unsure, or if it's a hard thing to differentiate, instead of using the second derivative, remember you can always draw up a table of values and just investigate either side of the inflection point, stationary point I should say, and then work out, oh okay, it's decreasing, then it's increasing, so it must be a maximum. So that's if it's a more difficult function to differentiate. And similarly with inflection points, the first criteria is finding the second derivative equal to 0. But then, depending on how you do it, we could have used our third derivative test. Third derivative is not equal to 0. Or again, if it's a difficult thing to differentiate, draw up a table of values and have a look at what's happening at concavity. Because remember, inflection points is when concavity changes. Reality is, most of the curves, we don't usually bother finding inflection points, because a lot of the times it's obvious there's going to be one, because if you've got a turning point here and a turning point here, well, it must inflect somewhere in the middle. Right? So I usually only find them if they ask me to. And then our horizontal point of inflection, where it's both stationary and an inflection point, the classic one being our cubic. Okay, increasing or decreasing curves. The slope of the tangent tells you whether a curve is going up or down, because if a curve's going up, the tangent must have a positive slope. If a curve's going down, the tangent must have a negative slope. So we can, if we've got the first derivative is greater than 0, I know the curve's going up or it's increasing. If it's less than 0, curve's going down or decreasing. Don't forget our idea we saw in conics of implicit differentiation. That can save time, rather than making y the subject. So let's go back to our x cubed plus y cubed is equal to 1. And if we had to draw this curve. Now, again, I don't want to make y the subject. That's going to make life too hard for myself. So what sort of things do I notice? It's got symmetry in the line y equals x. Because I can interchange the x and y's, it would stay the same. So, whoop, there it is, y equals x. There's my axis of symmetry. Okay. Now, the x-intercepts and the y-intercepts are very easy to find in this curve. So 1, 0 and 0, 1. And that makes sense too because of that symmetry around y equals x. Okay, let's plot those in. There's 0, 1, and there's 1, 0. Now, this may not be immediately obvious to you. The curve is going to be asymptotic to the line y equals negative x. Here's how I worked that one out. If I did make y cubed the subject, I could say, well, y cubed is 1 minus x cubed. Well, if that's true, y cubed can never equal minus x cubed. Therefore, y can never equal negative x. And so I've got an asymptote of y equals negative x. So, let's draw that one in. So that's now an asymptote. I've got an axis of symmetry, a couple of turning points. I know I bend towards the asymptote. What else can I do? Well, if I do differentiate this to try and look for stationary points and things like that, so I end up with the derivative is minus x squared on y squared. So I know that at 0, where were my 2 points? Here they are. 0, 1, I would have a stationary point. The derivative would be 0. Whereas at 1, 0, I'll end up with a critical point. Okay. Again, that makes sense if you think about it, because if it's symmetric in y equals x, one of those would have a vertical tangent, one would have a horizontal tangent because of the reflection. Okay. Now, the other thing it tells me, which you might not have noticed, but if I've got minus x squared on y squared, then the derivative is always negative. Doesn't matter what I substitute in. So this curve is always going to be decreasing. So I know the curve is going down for the whole domain. So what does it end up looking like? There it is. So that's x cubed plus y cubed is equal to 1. So we do tend to look at, that's probably one of the more unusual curves that we might see when they're in implicit form. Okay.